Hey everyone, and welcome. So, if you've ever found yourself listening to people talk about tech and noticed that the terms artificial intelligence, machine learning, and deep learning all seem to blur together, well, you are definitely not alone. Today, we're going to cut through the noise, demystify these buzzwords, and really get to the heart of what each one is. Let's dive in.
So, right off the bat, what is the real difference? Are they just fancy synonyms for the same thing? Nope, not at all. Not only are they different, but they actually fit together in a really specific way, kind of like a family tree of ideas. And once you see that structure, honestly, the whole field starts to make a lot more sense.
You know, the best way to visualize this relationship is with a set of those Russian nesting dolls. Just picture it. AI is the biggest, outermost doll. You pop it open, and inside you find the next doll. That's machine learning. Then you open that one, and you find the smallest, most specialized doll, deep learning. This one simple metaphor is going to be our guide through this whole thing.
Okay, so let's start with that biggest doll on the outside, artificial intelligence. This is the granddaddy of them all, the big idea that kicked off this entire journey decades ago.
So AI is the huge umbrella term. It's really any system or any machine that can mimic human cognitive functions. We're talking about the big stuff here. The ability to learn new things, to reason and draw conclusions, and even to correct its own mistakes along the way.
What's really interesting, though, is how early AI worked. It didn't learn like we think of it today. It was all rule-based. You'd literally have human experts sitting there programming these enormous decision trees with thousands of if-then-else statements, like if a patient's temperature is over 100 and they have a cough, then diagnose the flu. It was all hard-coded logic.
And right there, that's the fundamental problem. These systems were incredibly brittle. They worked flawlessly as long as the situation fit the rules perfectly. But the second you threw something new, or a little bit ambiguous at them, something the programmer hadn't thought of, they just collapsed. They had zero ability to adapt. And that set the stage for a much, much smarter approach.
So, to fix that brittleness problem, we've got to open up our big AI doll and look at the next one inside, machine learning.
Machine learning completely flips that old model on its head. See, instead of humans writing the rules, ML algorithms learn the rules for themselves by digging through huge amounts of data. The whole point is to find patterns and make decisions without a person needing to step in and tweak the code every time.
This quote just nails it. We stopped programming the logic directly and started programming systems to learn the logic on their own. It was a total game changer, a really revolutionary shift in thinking. But as powerful as it was, this new method hit its own roadblock.
And that roadblock has a name: feature engineering. A feature is just a measurable piece of data, like the price of a house or the sender of an email. The problem with traditional machine learning is that a human expert has to manually pick out all these features, clean them up, and get them ready before the algorithm can even start working. It's a huge, manual, time-consuming job.
Let's make this really concrete with a spam filter. So first, a person has to sit down and decide what features might signal spam. Things like, the word free or a subject line in all caps. Then you have to write code to go through every single email and pull out those specific features. And only then can the algorithm finally do its job. You can see the problem, right? The machine is only ever as smart as the features the human thought to give it.
Now, this approach works okay for things like spreadsheets, but it completely falls apart with complex stuff like images. Seriously, how would you even begin to manually define the features of a cat in a photo? Are you going to try to write rules for whiskers and pointy ears based on raw pixel data? It's basically impossible. And this very limitation is what forced the next big leap.
So, to solve that impossible cat picture problem, we open up the machine learning doll. And inside, we find our last, most specialized layer, deep learning. This is the technology that automates that whole messy discovery process.
Deep learning is a very specific type of machine learning. What makes it unique is its architecture, which is actually inspired by the neural networks in our own brains. The deep part isn't just a buzzword. It literally means it has many, many layers of these artificial neurons stacked on top of each other.
And here's the magic trick, the big revolution. Deep learning gets rid of manual feature engineering. The network learns the important features all by itself, in a hierarchy. So the first layer might just learn to spot simple things, like edges and colors. The next layer combines those edges to see shapes, like eyes and noses. The layer after that combines those shapes to see faces. It automates the whole thing, from simple to complex.
Now, all this amazing power comes with a price tag. For one, deep learning models are incredibly data hungry. We're talking millions of examples to learn effectively. They're also computationally intense. You need really powerful hardware like GPUs to run them. And finally, they have what's known as the black box problem. They can give you an amazingly accurate answer, but good luck figuring out why it made that specific decision.
Okay, so we've got the what, we understand the hierarchy of AI, ML, and DL. But let's switch gears and talk about the how. How do these systems actually learn? Well, it turns out there are three main styles that apply to pretty much all of them.
First up is supervised learning. This is basically like learning with a teacher. You feed the model data that's already been labeled. This picture is a cat, this one is a dog. And its job is to figure out how to predict those labels for new data. Then there's unsupervised learning. Here, there's no teacher, no labels. You just dump a mountain of data on the model and say, find something interesting. It has to discover the hidden patterns all by itself, like grouping similar customers together. And finally, you've got reinforcement learning. This is all about trial and error. Think of a robot learning to walk. It gets a reward for a good step and a penalty for falling over, and it slowly learns the best strategy to get the most rewards.
All right, let's get practical. With all this in mind, how do you actually choose between traditional machine learning and deep learning for a project? It's really not about which one is better overall, but which one is the right tool for the job you have.
It really all comes down to one crucial trade-off: interpretability versus accuracy. Traditional machine learning models are highly interpretable, meaning you can easily look inside and see why a decision was made, like why a loan was denied. Deep learning, on the other hand, often gives you way higher accuracy, but it's that black box. You get the right answer, but you don't always know how it got there. That's why traditional ML is still critical in regulated fields like finance, while deep learning is king for stuff like image recognition.
This chart breaks down those practical differences even more. If you've got a small or medium-sized dataset, traditional ML is your friend. It's fast to train, runs on a normal computer, and it's perfect for structured data, like spreadsheets. Deep learning is the heavy hitter you call in for massive, messy datasets, like images, audio, or text. But be prepared. It needs that special hardware and can take days or even weeks to train.
And this chart right here shows maybe the most important difference of all. See how the performance of traditional ML just plateaus? After a certain point, throwing more data at it doesn't really help. But look at deep learning. Its performance just keeps on climbing. The more data you feed it, the smarter it gets, which is exactly why it has exploded in our age of big data.
So let's tie this all together. The key takeaway here is that the choice between ML and DL isn't about which one is better in some abstract sense. It's a strategic decision. It all depends on your specific problem. Got a massive, messy dataset and all you care about is raw performance? Deep learning is your answer. Got structured data, a normal computer, and you absolutely need to explain your results? Traditional machine learning is probably your best bet. It's all about the right tool for the job.
And that leaves us with one final, much bigger question to think about. As these powerful systems get woven into every part of our lives, from medicine and finance to the justice system, we are facing a fundamental choice. What do we value more, the incredible, often superior accuracy of a machine, or our human ability to understand exactly how and why it makes the decisions it does? The answer to that question is going to shape the world